Mobility, agility, safety, speed. These are all key factors in the unmanned exploration of the surface of the planet Mars. In an environment hostile to humans, remote-controlled robots are a main source of crucial information. The more quickly, independently, and reliably they can move across the surface, the faster and more reliably knowledge about the red planet can be transmitted. The aim of the FASTER project, a collaborative technology project with 6 partners from 5 different countries, was to develop a powerful land rover system for the exploration of Martian terrain. FASTER stands for Forward Acquisition of Soil and Terrain Data for Exploration Rover, a robotic system with a high degree of autonomous mobility. Since August 6, 2012, the current NASA rover mission Curiosity has been successful in traversing the landscape. Meanwhile, the Opportunity rover has already covered over 40 kilometers. But not every mission has gone smoothly. Some fully functional rovers have become stuck in Martian terrain, as did Opportunity's sister rover Spirit. After over 5 years of surface exploration, the Spirit rover became permanently stuck in a patch of soft soil in 2009. The space industry is searching for ways to prevent these glitches.
Mechanics is, let's say, the science of interaction between a vehicle or tool and soils on Earth, but also on other planets. You first of all needed to design a vehicle like a planetary rover, so to be able to size the wheels, the number of wheels, so you have adequate mobility. On the other hand, to predict, to assess the safety of the mobility and the bearing strength of the terrain or trafficability. The ideal soil sensor is able to warn you of hazardous terrain conditions ahead of the rover mobility. This kind of technique would really enable you to go quicker with a rover, to pass more distance per time, because it would make missions so much more efficient.
Today we are in the Mars Yard. The Mars Yard is a new facility at Airbus. It opened in March this year, in 2014. This is quite a long building, as you can see behind me. It's between about 13 to 14 meter wide and about 35 meter long. And as you can see behind me, it actually replicates or tries to replicate aspects of the surface condition on Mars, especially to develop specific aspects for the ExoMars mission and the ExoMars rover itself. As you can see, there are rocks, sand and lighting conditions that we are trying to use to develop especially all the aspects of the guidance, navigation and control for the ExoMars platform. And today we're using this facility as part of the FASTER project to provide us with a realistic environment to work in. FASTER here is trying to develop all the tools necessary to quantify and characterize the soil before the primary rover actually gets to its location. So for the FASTER project, we are dealing with 2 main platforms. First, we've got the Scout, and we've got the primary rover. So the primary rover represents the rover carrying the payload over the course of the mission. And to replicate this platform, we're using the platform we see behind me called Bridget. Bridget is a platform that was developed as part of the ExoMars program initially to test all aspects of the locomotion system. This platform is very realistic in terms of its locomotion system. You can see it doesn't actually have just 4 wheels, it's got 6 wheels, and the suspension system is completely passive. That means that it doesn't have springs or anything like that, and it's very representative of what ExoMars is going to use, and similarly what the American Mars Exploration Rovers are using. It's called a passive suspension system. As part of the faster testing, we use on the main platform a system that's very similar to the ExoMars guidance navigation control. We want the scenario to be as realistic as possible. The rover has to understand its surrounding. It will capture a number of images that are used to create 3D data and a 3D model of its environment.
Within the FASTER project, we are developing the Scout rover. The Scout rover is carrying 2 different sensor systems as payload, saying the wheel-leg soil interaction system and the dynamic cone penetrometer.
That was the part that wasn't working.
We are following the primary rover's path in front of the primary rover to ensure that the way is safe for the primary rover to go on that trajectory. Having the 2 rovers in one system is actually quite new for a space exploration mission, and therefore this adds a bit of complexity to the whole system as you have 2 rovers running in one mission. We are using quite a novel approach for locomotion. These are hybrid-legged wheels in the front, and they are able to overcome pretty high obstacles, pretty steep slopes, and perform quite good on loose soil as well as gravel or unstructured terrain. The 2 rear wheels are a new development from our side. They are spherical helical wheels which allow to steer the rover by side-to-side steering, shifting the point of rotation to the front axis. Furthermore, we have an IMU on board of the Scout rover, and therefore we are able to report our location back to the primary rover while we are doing the measurements. For precise position measurement, the Scout rover is also equipped with a marker in the rear, which can be tracked by the primary rover's camera system and can localize the Scout rover quite good with respect to the primary rover.
The idea behind Pathbeater is to measure the surface hardness of the soil. Pathbeater is proven to be a unique design. It's an idea that's been based on inspiration from looking at the way a blind man walks through the street with his stick. The second thing is that it also has some affinity to insect life, like a beetle, with its feelers, which navigates by touching the local surface. Well, you see the feelers on a beetle moving up and down or side to side. So I think, okay, they are obviously using it as a touch system, creating a map for themselves, which direction to turn when they meet an obstacle. We also wish to measure the surface properties in front of both sides of a rover wheel. We did this by having arms which could be deployed forwards, and at the tips of the arms were what we call penetrators. The movement of the arm is dictated by a simple spring device operated by a cam, and the tip of the arm with its penetrator penetrates the surface of the soil. We measure the forces, the accelerations at that tip, and from that we can determine impact loads. The rest of the arm is a form of flexible device which is fitted with strain gauges, and this measures during the impact it bends. It can bend in both directions, and we measure the bending strains by means of so-called strain gauges. This information is then compiled and interpreted to determine the bearing strength of the soil when the penetrator impacts, and secondly, through the spring, it holds the penetrator into the top surface of the soil for some distance before the arms are raised again.
The Soviet lunokhod rovers had an instrumented wheel in their backs, which could be deployed on command, and it would document the soil strength. Okay, but that was only after the rover had already driven over a particular location. And we are turning this around, so we have the test wheel in the front in the driving direction. So we measure the terrain physical properties like half a meter in front of the rover during driving, and the software calculates in real time the terrain properties, and then we can predict, using those parameters, predict in real time the mobility, the traction of the rover. The wheeled bathymeter has 3 indicators to distinguish between soft and strong soil. So one is the sinkage of the test wheel, which indicates bearing strength of the soil. The other indicator is the shear strength, which is measured with the wheeled bathymeter when the brake blocks the test wheel and pushes it through the soil. And there is a third indicator, which is the slippage of the rover wheels, because the wheeled bathymeter acts as an odometer wheel, and from this you calculate the rover slippage. And if it increases the rover wheel slippage, then this also indicates a weak soil, soft soil. If we are able to generate this prediction of the mobility of the rover over soil in the terrain during the mission, then we are able to actually be faster in mission operations. So it is possible for the rover to more confidently move. You need less intervention from the ground control center, so less human intervention. The benefit is more autonomy on board the rover on Mars, which increases the speed of the overall rover mission.
We have the wheel leg system. The wheel leg itself is part of the Scout rover. There will be 2 of these as primary drive units, one on either side of the front of the Scout rover. With the wheel leg system, we're measuring sinkage. We're trying to mimic the same pressure loading of the primary rover with a smaller contact area. And we're additionally getting the load information on the drive motor and IMU information. One thing that we did for this system to modify it from the original is we made these special load testing feet. And as you can see from the side profile, there is a small ridge of varying thickness along here that mimics the load pressure on the soil surface, similar to what we would see from the large primary rover, but with the small mass of the Scout. And those combine these values together to create a trafficability assessment, or how fit is the soil for actual driving on. If this device yields some intermediary results where it's not conclusive whether the terrain is trafficable or not, we will then deploy this, which is a dynamic plate mechanism. Within here we have a drive motor and an impact hammer mechanism. As the motor turns, a hammer is raised against a spring and fires down into an impact plate, which causes periodic vertical impacts that drive this device into the ground. Those information would then be fed back to the primary rover for decision making on its part, to then update its path planning system to determine a safe way to travel. So although all of the different sensor systems have the same goal in mind, they each approach the task from slightly different methods and backgrounds and ways of looking at how could we possibly test the soil.
My main involvement in FASTA is associated with the routines that generate the rock detection. So essentially we're part of a process that identifies hazards for the rover as it moves across the terrain. To talk about the role of the stereo camera, maybe it's helpful to kind of describe the process a little bit. In essence, we use a stereo camera in navigation or hazard detection to be able to generate depth perception in the scene. So what it's doing is helping us work out how far objects viewed from the rover actually are. And in fact, to handle rock detection, we apply two different techniques. We look at the scene firstly and analyze it for what's called saliency. So we're trying to find things that are interesting in the scene that may well be rocks. Having identified those points in the scene and located them in the scene, we use the information from the stereo cameras, and in particular a quantity called disparity that allows us to work out how far those objects are from the moving rover. So one of our challenges here is to be able to distinguish the rocks from the rest of the environment, picking out textures which don't rely too much on different colours because it's a rather monochromatic scene. On the other hand, we don't want our textural information to be so sensitive that it would also register, for example, the tracks of the Scout in front of the main rover.
The main challenge in a scientific point of view is to build a model of the environment that is not known. I'm getting information from all the soil sensors, which should be useful for path planner to plan the most optimal but safe path for the robot movement. Data fusion system is for integration this data, needs to put this data in a correct order, in a correct space, draw the path of the sensors with readings, with measurement values on a trafficability map.
Well, the most important part of what we're doing at Space Application Services is building the brains behind the primary rover and also how it deals and coordinates with the smaller Scout rover. Earlier in the project, we also led, along with the help of all the other project partners, the definition of the concept for the FASTA mission and how the two rovers should work together to achieve their objective. And now we're trying to get this working. Well, as with any other project on a large international scale, where the people working on the different parts of the project are spread over many countries, it's not that easy to have things come together in the snap of a finger. Here we've been lucky that all the partners are very cooperative and willing to go the extra mile to get the system running.
Over the course of the project, members of the consortium pooled their efforts to design faster, taking it through the stages of concept, prototype, design, fabrication, and analysis. The collaboration was made possible by the 7th European Union Framework Programme, which offers funding schemes for projects in science and technology to teams that are multinational and diverse in expertise. The German Research Center for Artificial Intelligence, or DFKI, led the project. Other partners are the University of Surrey and Airbus Defence and Space, both in the UK, Space Application Services in Belgium, Liquifer Systems Group in Austria, and Astri Polska in Poland. Working together, the teams not only developed a system for improved and safer mobility on Mars, but learned from one another, building multicultural working relationships and an environment for the robust exchange of knowledge and information.
Das war's.
Yeah, one of the interesting things for me personally is the multinational nature of this project. It shows how, I think, easy it is and what a good result you can get by working together with people from other backgrounds, with other experiences from different countries, and it shows the value of pulling together a multi-skilled and multinational team to execute these kind of larger common projects to get something as complex as this done.
For me, it's a challenge, and to see a design develop from nothing, just a sketch on a piece of paper, through to hardware that we already have, for me is quite an exciting process. It is an adventure. The whole thing is a major challenge for us.
There was a lot of excitement in conceiving and developing each of these different soil sensor systems.
Personally, I've spent 28 years working in space.
Yeah, my family and my brother should be proud of me.
Yeah, I think my mother and my parents are both very proud of me in terms of what I'm doing. Combining playing with toys and seeing things advance beyond where they are today. Always look at the best that can be done and try your hardest to get there. One of the great things about working on projects like this and in robotics is learning new things. New for me and hopefully new for other people as well. Building systems, building ideas that are not there today and that can hopefully play a big part in changing where humanity is tomorrow.